Verilog is a hardware description language abbreviated as HDL. It was insufficient to verify complex digital block functionality, and hence the VLSI industry experts came together and created a magic called SystemVerilog, which is more than a HDL, and it is called the hardware description and verification language abbreviated as HDVL. To transit from HDL to HDVL, a lot of concept has been borrowed from other programming languages like C, C++, Java, etc. These features by name similar to programming language counterpart. However, at application level, they are a bit different, keeping the hardware verification scenario in mind. We have an entire series on Verilog and a marathon also. From that concept, we will make transition to SystemVerilog in a systematic manner. This series will help you to grab the SystemVerilog language concept in slow and bite-sized episodes. We will do a comparative learning of the new features by comparing a SV feature with its Verilog and programming language counterpart. SystemVerilog has been long requested series from multiple viewers over a long period of time. We are happy to webcast this transition series in context of that. So stay tuned, stay focused. Hey guys, welcome back. In today's episode, we will be seeing through the bird's eye view of the changes, that is from Verilog to SystemVerilog, and this is a very short and sweet episode. In later episodes, we'll go in detail of each and every changes one by one. So without any further delay, let's begin. Today's menu is expected Verilog knowledge before learning SystemVerilog. So here we will touch base the points that you have to be well aware before you start to dive in for SystemVerilog. Next, we will go for the Verilog versus SystemVerilog for the fundamental difference and transition. Here we will tabulate these two, that is difference and transition. Next, in couple of slides, we will cover the points, that is new data types, operators and procedural statements in SystemVerilog, how these are different from Verilog. Next, we will talk about the process control and task plus function, the feature enhancements in SystemVerilog. Next, we will talk about the object-oriented paradigm that is adopted in SystemVerilog, which was not there in Verilog, through bird's eye view. Next, we'll go for the bird's eye view about the Testbench, Assertion and coverage. Sorry folks, there is a typo here. Next, we will have a bird's eye view about the hierarchy, modular based design and clocks, that is clocking blocks. Finally, we will touch base the enhanced APIs in SystemVerilog as well as formal semantics, which are new as compared to the Verilog. So this is the overall menu. However, the slides name will be different because we have compacted multiple slide names in one particular bullet here in this menu. And because of the slides content holding capability, we will split in multiple slides. So let us dive in. Expected Verilog knowledge before learning the SystemVerilog. You must know the module basics. Module is a syntax in Verilog. This is the key thing, that is we use module and end module. Also we use ports like input, output and in-out, that is the bidirectional ports in module. Next comes the data types. These are in Verilog like var and range, bit vectors and bus declaration using the third bracket. Next we have the assignments. We have continuous assignments which we do through the assign, and we have procedural assignments equal to for blocking and less than equal to symbol for non-blocking. Next we have procedural blocks, always for sequential and combinational logic. Next we have sensitivity list, which begins with @ like @ pausage of clock. All these are there in the Verilog, so you must be aware of these things. Next comes the control flow like this: if, else, case and loops like for, repeat, while. Next comes the hierarchy, module instantiation and port connection, positional and named. So you must be aware all of this from the Verilog basic knowledge. Test benches, stimulus generation using initial and always block, simulation constructs like $monitor, $display, and timing delays, which we do with the hash. Next comes the basic operators, arithmetic operator like plus and minus, bitwise operator like and, or and not, and logical, that is logical and logical or. Here is the thumbnail of the Verilog marathon that we have already published in our channel. The link is provided in the description below. In case you are not aware or you want to have a kickstart on Verilog, you can refer to this episode. It contains all the Verilog episodes, including installation of Vivado as well as Icarus Verilog that we have used for simulation of the Verilog codes, as well as there is a link in this video description from where you can download the Verilog codes used in the tutorial. So guys, this is the basic necessity. You must have the knowledge of Verilog before you start jumping into SystemVerilog, because SystemVerilog is much more vast than the Verilog and conceptually it is different. How? Let us explore in upcoming slides. So here we are done. Let's move on to the next slide. Verilog versus SystemVerilog, the fundamental difference. Verilog. Introduced in 1984. Verilog was created in 1984 to help describe how electronic circuits work, kind of like writing a blueprint for a building but for digital systems. It is known as Hardware Description Language, abbreviated as HDL. In 1995, Verilog was officially recognized as global standard by IEEE, and you can see here the standardization number. This ensures everyone could use it in the same way without having any confusion. Even though newer language exists, Verilog is still popular for designing older system and straightforward circuits because it's reliable and familiar. And basically, legacy systems have Verilog and simpler digital circuits are composed using Verilog. Primarily, it is used for structuring, modeling, simulating, and verifying electronic systems at RTL level. Verilog is mostly used to create and test digital design at level that focuses on how data moves or how signal moves and get processed within a system. That means for block level design, the Verilog is used. Now let us move on to the SystemVerilog. It was developed in early 2000s, and you can see Verilog was a HDL, right? That is the hardware description language, and SystemVerilog is hardware design and verification language, abbreviated as HDVL. SystemVerilog was created in 2000s to not only describe how circuit work like Verilog, but also to test and verify them. It combines design and testing in one language. Hence, it is called the HDVL, unlike Verilog, which is called HDL. You can see the V is missing in Verilog. That means the verification part is missing. And this verification part makes the SystemVerilog much more vast than the Verilog. Now let us move on to the next point. It became IEEE standard in 2005, and the standardization number, you can see it is mentioned here. Okay, in 2005, the SystemVerilog was officially recognized as a global standard, making it consistent and widely accepted for use. Today, the SystemVerilog is go-to choice for creating and testing large and complicated digital systems, such as those used in advanced SoC chips and programmable hardware. That means SystemVerilog used for large designs like ASIC or SoC and FPGA. It is essential for advanced modeling, comprehensive verification, supporting the full electronic system development lifecycle. Thus, the SystemVerilog is crucial for detailed design, thorough testing, and managing every stage of building of an electronic system from start to finish. So, here we have summarized both the Verilog and SystemVerilog. Here is a very compact summary. So you can see their timelines, their standardization, their targeted usage, everything. Now we are done with this particular slide. So we will move on to the next slide. Verilog to SystemVerilog transition. Here I would like to say a few words. Verilog has moved couple of generations and SystemVerilog has also moved couple of generation, and there is a cross coupling of them, and now the SystemVerilog is a superset of the Verilog. Let us see these timelines. Verilog versions. Verilog 1.0, that is from the year 1995, and they had standards numbers from 1364 to 1995. The first official version of Verilog was standardized in 1995, setting the rules and format for using it globally. Now we have another version, that is Verilog 2.0, that is 2.0 you can also say, in 2001, and its standardization numbers starting from 1364 to 2001. In 2001, the Verilog got a big update with many new features, making it more powerful and easier to use for designing and testing circuits. This was the first big change since it became public in the 90s era. Now these are the Verilog timelines. Now let us move on to the SystemVerilog generations. So here you can see the SystemVerilog 3.0, which was available in 2002, added high-level architectural model. So you can see the timelines, right? 2001 for Verilog and 2002 for SystemVerilog, because the SystemVerilog is actually the superset of the Verilog. That means within its hood, it contains the Verilog. In 2002, SystemVerilog introduced tools to help design circuits at a high level, focusing on overall structure of a system. SystemVerilog 3.1, which was released in 2003, had features like C language integration. It also contains advanced verification features. This means in 2003, SystemVerilog added powerful tools for testing circuits and made it easier to work with C programming language interface, bridging the software and hardware design. Then the next generation we have SystemVerilog 3.1a from the year 2000. So here we have multiple things like corrections, clarification, further enhancements, including VCD and PLI specification. So this sums up in 2004, this version fixed many previous issues, clarified previous features, and added more improvements like better support for tracking signal changes through the VCD, that is value changed dump, and extending its functionality like PLI. In Verilog, we already have talked about this VCD and PLI, and now they are integrated with the SystemVerilog. So here we are done with the timeline and generation of Verilog and SystemVerilog and what happened in one generation to another. Now the SystemVerilog is a superset of the Verilog. That means SystemVerilog has all the features of Verilog plus some additional features. So after 3.1, there are multiple IEEE versions are there, and they are available through the IEEE website. And this particular version, that is SystemVerilog 3.A, the LRM is called a legacy LRM. That means this LRM had indexed the vastness of the SystemVerilog. Later, the manuals which are available through IEEE, they are more vast. However, this has, I think you can say, summarized version of the vastness. However, it is vast. It seems oxymoron, but it's true. Now we are done here. Let's move on to the next slide. Now we will look into the incremental updates in SystemVerilog with respect to Verilog, and this approach we are going to take is from language perspective, because learning SystemVerilog has two approaches. One, you learn it for the verification purpose, that is a verification approach, and there is another approach which is called the language perspective. In between these two approaches, you have to take the language perspective first, because if you do not know the language, you cannot use it in the massive scale of verification. So we will start with the language perspective in this particular series. So let us move on to the next slide. New data types in SystemVerilog. First of all, extended data types. And these data types helps for encapsulation and code compactness. New types were added to make the code more organized and easier to write by grouping multiple data together, because this will help in verification. Later when we go for the verification, you can understand this. But from language perspective, you can see that there are a lot of extended data types which was not present in Verilog, now are present in SystemVerilog. C data types. Those who know C language, I think every one of you probably learned the first programming language as C now, and C has int, typedef, struct, union, enum, all these things. SystemVerilog includes types similar to those found in C programming language like integers, group data called structure, shared memory called union, and predefined sets of values called enum. So from C, all these concepts are borrowed in the language perspective. We are not talking about the verification perspective. There we will see how these are vast than C. Other data types like bounded queues, various logic levels, that is 0, 1, X and Z. Also bit, it is a new type, tagged unions. If we sum up, additional types like queues with limits, signals with more digital states, and unions with labels for easy identification are introduced in SystemVerilog. And all these are introduced for the sake of verification. But from language perspective, you must have the total knowledge, which you can then apply in a practical application level for the verification. Dynamic data types. We have string, classes, dynamic queues, dynamic arrays, and associative arrays. If you go through our marathon or the Verilog playlist that we have, link is provided in the description of this video. You'll see we had tried to capture string with the reg there. However, classes were not there, dynamic queues were not there, dynamic arrays were not there, associative arrays was not there at all. But all these are introduced in system verification for data mining for the verification purpose. And this data is, you can imagine, the digital systems, subsystems and blocks they are sending among each other. So we need these data types for storing those received or transmitted data and do the further analysis. Dynamic casting and bit stream casting, they were added for flexibility. These features allow converting one type of data to another, rearranging bits easily for different uses. Automatic or static specification per variable instance. In SystemVerilog, you can now decide each variable whether its memory is dynamically managed or fixed from beginning. This gives more control over how this is used. So this is another thing that has been implemented in SystemVerilog, and this is also for the sake of verification. From language perspective, this is very much similar to the language you know like C, right? And here I would like to point you one thing, that if you remember malloc, right, from C, in case you do not, go ahead and check back the books that you have read on C, or you can search it on internet. So this similar kind of dynamic capability, however, we are not having a malloc here exactly, but we have the features implemented in SystemVerilog. So done here about the new data types that are in SystemVerilog, and you have a bird's eye view of what are new in SystemVerilog. Now let us move on to the next slide. Here in this slide, we'll talk about the operators and procedural statements that are with SystemVerilog and was absent in Verilog. Operators like extended operators, we have void, equality or inequality, stream, and membership. And this sums up in SV new operators were added, like those to check approximate matches, void equality, process data streams, or see if any belongings to a group, that is setting a membership. Next, we have built-in methods, that has extended the language capability. In that, if we sum up, the SystemVerilog includes built-in functions to make certain tasks easier, like manipulating data or arrays. And this will be seen in the object-oriented part. Okay. Next, we have the operator overloading, and here we customize the operator. And if you sum up, in SV, you can define how certain operators like plus or multiply, that is asterisk, behave when used with specific types of data, making them more flexible for various operations. Now we are cleared with the operators, and we will move to the procedural statements. Extend statements, enhanced loops here, for each, pattern matching, you know about the regular expression, C like jump statements. So what are all these? SV has loops were improved with options like for each for simpler iteration, regular expressions for matching patterns in data, and familiar jump commands like break and continue for precise control of the loops. Final blocks executed at the end of simulation. SV has special sections of the code called final blocks that run automatically when the simulation finishes. It is useful for cleanup tasks or final reports. So this is a kind of footer-like thing. So we have header footer concept in maybe in documents, right? So there we have footer. So this is very similar to the footer. Next, we have the extended event control, sequence events, and control. So if we sum up, ASV has better tools or features, you can say, to manage and synchronize events during simulation, making complex behavior easier to handle. Don't worry, we will see in vivid detail in later upcoming episodes. So we are done with this particular slide, and here we have covered the operator level enhancements and the procedural level statements, the enhancement around this and enhancement around this. We are done with this particular slide, so let's move on. Process control and the task and functions. Process control. We have enhanced the control, extension to always blocks or synthesis consistency. And this is very important. ASV made improvements to always blocks and ensure they work better for creating hardware designs that match the intended behavior during simulations. For your knowledge, ASV has multiple types of always blocks for various usage. We'll not disclose them here. In later episodes, we'll disclose with you. Fork join extensions. These are for modeling pipelines and improve control. And if we sum up, the ASV has new avatars of fork and join, completely different from that already what you have. These may look similar, but these are very different at application level. In ASV, new avatars of fork and join make it easier to run multiple tasks at the same time, such as simulating data pipelines and managing processes more efficiently. We'll go discuss them in detail in later episodes, so we are done with this bullet. Fine grain control, detailed task and function management. In ASV, mechanisms were added to give precise control over how the task and functions operate, helping manage complex processes better and easier for the verification entity. We are done with the process control and now move on to the task and functions. C-like functions. C had void functions, right? You remember? And C had pass by reference as well as default optional arguments. So lot of flexibility was there in C. And SystemVerilog functions adopted all these from C, supporting features like void, that is no return value, passing variables directly by reference, and using optional or default values of the arguments. So this is a language perspective that SystemVerilog has adopted from C. DPI functions. DPI is nothing but the direct programming interface. It helps import and export capabilities for the direct programming interface. And if we sum up, in ASV, the direct programming interface allows easy interaction between SystemVerilog and other programming language like C, making it simple to integrate external code and enhance the verification capabilities. That means you don't have to go for the language modification or the software modification. Through these DPI ports, you can plug in external codes like C codes and you can enhance your capability. That means the verification capability. So in this slide, we have talked about the things that have been adopted regarding process control and task and functions in SystemVerilog. We are done with this slide, so let's move on to the next slide. Object-oriented programming. Now here I would say that object-oriented programming is a vast thing. We cannot capture everything in a single slide. However, here we are trying to just give you some brief bird's eye view. So first, in the object programming language, we have classes that has abstraction, encapsulation, and safe pointers. In OOP, classes help to organize the code by grouping release data and functions, hiding unnecessary details, which is called encapsulation, and safely managing object references called pointers. Now we have interfaces. This helps connections in a manner that they are enhanced by new feature called interface or interface object. You will have the details, but connecting the pins to pins was a very difficult thing in Verilog, and that has been made easy here. Encapsulation. So this facilitates communication oriented design, and this is very simple to view because in our digital design we have blocks, sub-blocks, and we have unit level designs. So there is a lot of communication happening. And interface makes it easier to manage communication between parts of our design by grouping related signals and ensuring clean, organized connections. These are more compact and easy to use as compared to its Verilog counterpart and less error prone. That means as a human being, you have almost 0% chance of errors in the connections like the bus connection or the pin connection or both. We'll go in detail in the later episodes. Here we have just touched base the object-oriented programming and interfaces. So we'll move on to the next slide, that is Testbench, and excuse me for this typo. So here we'll talk about the different Testbench, assertion and coverage. Testbench support. Automated Testbench. Now in SystemVerilog, we have randomization for constraints, synchronization via semaphores and mailboxes. And if I expand this line, SV Testbenches can now automate testing with random value inputs that follow specific rules and restriction called constraints, and manage communication between parts using semaphores and mailboxes, which are also new feature in SV. Event extension, event variables and sequencing. And we expand this concept like this. In SV, new features were added to handle events. Events means digital events that happens inside the circuit more flexibly, like storing events in variables and setting up sequences of these events for testing. That means we have a precise control over the events. Scheduling semantics, clarification and extensions. And if we expand this concept, in SV, improved rules and features were introduced for how the tasks are scheduled during simulation, ensuring more accurate and predictable testing. So here we have talked about the Testbench support. Let us move for the assertion and coverage. These are new features totally. This assertion and coverage. These two are totally new in SV. They were not there in Verilog in any form or shape. Now let us focus on the assertion mechanism, verifying design and functional coverage. And if we expand the concept, SV assertion check if a design behaves as expected, while functional coverage measures how thoroughly the design has been tested. Don't worry, we'll go in detail. From language perspective, you must know that these are things which are completely new. Property or sequence declaration, assertion and coverage statements with action blocks. In SV, you can define specific behaviors or conditions called properties or sequences for checking correctness, include actions to take when these conditions are met or fail. So here again we are talking about precise control, which is used for verification. So here we are done with this particular slide. Let's move on to the next slide. Hierarchy, modular based design and clocks. Hierarchy and modular design, enhanced hierarchy. What we have here, packages, nested modules and external modules. SystemVerilog allows better organization of code with reusable packages, modules within modules called nested, and external modules that can be defined separately. Hence, you get a lot of flexibility. Port declarations. We have support for interfaces, events and variables. Ports which connect different parts of a design now supports interface, grouped connection, the meaning of the interfaces, events and variables for more flexible communication. Such easy to use for feature reduces cumbersome process of verification. Next, we have root, that is clear hierarchical reference. $root proves a top-level reference for organization and accessing design elements, making it easier to navigate complex designs. Please don't confuse this with the Linux super user root. Okay. In later episodes, we will discuss this root in detail. Cycle-based functionality. These are also completely new features. Clocking blocks. We have clocks and those can be complex in digital design. So we have clocking blocks. Cycle-based signal drives the samples. Synchronous samples are there. In SV, clocking blocks help manage signal based on clocking cycles, ensuring proper timing for driving and sampling the data in synchronous designs. So we have a lot of precise control over the clocks in SV because this is verification. Now we have race-free context, that is safe program execution. These features were added to prevent timing conflicts called racy conditions during program execution, ensuring accurate and reliable behavior in simulation. So here we have discussed the bird's eye view for the hierarchy and modular design features and cycle-based functionality. Those are new in SV. We are done with this particular slide, so let's move on. Enhanced APIs and formal semantics. So we are now going to the different part of the SystemVerilog where we have APIs. In general, APIs are like plug and play ports of the software or a language. That means we have plug and play kind of features. DPI or the direct programming interface. It has efficient interoperation with other languages like C. In SV, the direct programming interface called DPI allows SystemVerilog code to interact smoothly with another external codes of programming languages like C, making it easier to integrate with the external code and working very much hands-on synchronously with the external codes. Next, we have Assertion, Coverage, Data Read APIs. These are tools for verification and data handling. These SV APIs provide functions to help verify correctness of design, check how well they are tested, that means the coverage, and manage the data during simulation. Next, VPI extensions. Nowadays, these are hotcakes for SystemVerilog constructs. VPI or Verilog Programming Interface extensions allow better interaction with SystemVerilog constructs, helping developer work with design more effectively. These are very popular in recent times. Concurrent assertion formal semantics. Here we have enhanced support for concurrent assertions in verification. That means we have one particular assertion that is stating something, another assertion that is stating something, and in timeline both are on the same point of the time axis. In SV, these improved support for checking multiple conditions at same time, that means concurrent assertion during verification process, making it easier to detect issues in complex systems. So here we have talked about the plug and play feature like APIs and assertions, right? All these things are enhanced in SystemVerilog. So today we have covered the bird's eye view of all the things that have been introduced in SV. Either they have been fetched from various programming languages or they are altogether new in SystemVerilog, and the concepts are very necessary for the verification. So we are done with this particular slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.